Now, what's critically damped? It must be the case just in between these two. Neither complex nor the roots different. It's the case of two equal roots. So r squared plus ar plus b equals 0 has two equal roots. Now that's a very special equation. Suppose we call the root, since all of these, notice these roots in this physical case, the roots always turn out to be negative numbers or to have a negative real part. I'm going to call the root a. So r equals negative a, the root. A is understood to be a positive number. I want that root to be really negative. Then the equation looks like, the characteristic equation is going to be r plus a, right, if the root is negative a, squared because it's a double root. And that means the equation is of the form r squared plus 2 times a r plus a squared equals 0. In other words, the ODE looked like this. The ODE looked like y double prime plus 2ay prime plus, in other words, the damping and the spring constant were related in this special way. That for a given value of the spring constant, there was exactly one value of the damping which produced this in-between case. Now, what's the problem connected with it? Well, the problem, unfortunately, is staring us in the face when we want to solve it. The problem is that we have a solution, but it is y equals e to the minus at. I don't have another root to get another solution with. And the question is, where do I get that other solution from? So the way to do it is, the solution we know is e to the minus at. So we're going to look for a solution to this differential equation. That's the differential equation. And the solution we're going to look for is of the form e to the negative at times u. Now you're going to have to make a calculation like this several times in the course of the term, so that do it this way. Y prime equals, differentiate, minus a e to the minus at u plus e to the minus at u prime. And then differentiate again. The answer will be a squared, you differentiate this, a squared e to the negative at. I'll have to do this a little fast, but the next term will be, minus, so this times u prime, and this, from this you're going to get another minus. So combining what you get from here and here, you're going to get minus 2a e to the minus at u prime. And then there's a final term which comes from this e to the minus at u double prime. Two of these because a piece here and a piece here combined to make that. And now to plug into the equation, you multiply this by 1. In other words, you don't do anything to it. You multiply this line by 2a, and you multiply that line by a squared, and you add them. On the left-hand side, I get 0. What do I get on the right? Notice how I've arranged the work so it adds nicely. This is a squared times this, plus 2a times that, plus 1 times that makes 0. 2a times this, plus 1 times this makes 0. All that survives is e to the at u double prime, and therefore e to the minus at u double prime is equal to 0. So please tell me, what's u double prime? It's 0. So please tell me, what's u? It's c1t plus c2. Now, that gives me a whole family of solutions. Just t would be enough. Because all I'm doing is looking for one solution that's different from e to the minus at. And that solution, therefore, is y equals e to the minus at times t. And there's my second solution.